So thank you for giving us the opportunity to present something today about city emission inventories. We think it's a very important topic, so very excited to present something here today. My name is Ingrid. I work at TNO, and yeah, our main job is to compile emission inventories. We do that for Europe, but now also going to start with city emission inventories. So next slide, please, that I will introduce the topic of today. Oh, next slide, please. You see here at the bottom left, the figure depicting the MVS capacity of Copernicus, and MVS stands for Monitoring Verification System. And you see that emissions are very central in this figure. The idea of this MVS is that you use this prior information on emissions and other fluxes, combine them with observations and models to estimate real emissions by weighing all this data. So this prior information is very important. Although this is for a global application, you can also do that for cities very well. Actually, cities emit a large quantity of global anthropogenic greenhouse gas emissions and are therefore especially an interesting target for MVS. And also for climate mitigation. But to understand where you can gain most from climate mitigation, you first need to know where emissions take place, when they take place, what type of activities are mostly responsible for emissions, and what are the main drivers. So for example, if you have a city where a lot of public transport is being used, electrification of this transport actually makes a lot of sense, and you can reduce emissions quite a bit. But if people in the city mostly take their own car or maybe go by bike, then it doesn't really make a difference. So you need to understand this urban emission landscape. And city emission inventories can play an important role in that, and also for setting climate ambitions. Next slide, please. So in this webinar, we will present state-of-the-art emission inventories for the 3 pole pilot cities. We start with Munich. For Munich, there is not a spatially explicit city emission inventory available yet. So this is where most of the work will take place in the project. But to understand where we can go to, we also introduced the inventory for Paris. This inventory is based on a lot of local data, so it's actually a great example of what we want to do for Munich. And then we also introduced the inventory for Zurich, which is a vector-based inventory, and it really shows all the range of possibilities for compiling city emission inventories with increasing level of detail and increasing complexity. And in addition to this, we will also discuss some of the main challenges that we face in compiling emission inventories. Next slide, please. So we'll start with Munich. As I mentioned, Munich does not have an emission map yet. So our first approach is to downscale existing emission data. We have compiled an emission inventory in the Horizon 2020 Verify project, which has a 1 kilometer resolution. Munich is in that domain. And we will use that to downscale to 100 meter resolution for the city of Munich using proxy data. The advantage of this method is that you can do this for any city without an emission inventory, because you can simply use whatever proxy data is available. So as a first estimate, this is a very good option. On the left-hand side, you see an example of how this downscaling works. In the left figure, you see the officially reported road transport emissions for the Netherlands at a 1 kilometer resolution. And we have downscaled this to 25 meter resolution for the city of Eindhoven using OpenStreetMap data. This also includes some information on road type, but there's no further information on traffic intensity included. So it's just, you basically put the emissions where the roads are. And then you see this very nice structure of roads and highways. So because we start with this, this regional inventory, which actually makes use of national reported emissions, this city inventory will be fully consistent also with country reports and with the regional inventory outside the city boundary. So it's very easy to nest it for regional modeling as well. And then on the right-hand side, there's another example. It's also for the city of Eindhoven. And here you see an emission map of residential heating. It's also 25-meter resolution. And well, in this example, you can, for example, use a population density or information on addresses to put the emissions on the right place. So you basically put them where buildings are, which makes sense. But in this case, we also have information, for example, on energy labels. And if you have this information, you can simply add it to the downscaling approach. If you do not have it, that's also fine. So there's a lot of flexibility in this method. The main downside, though, is that you still have a gridded inventory. So you need to define the resolution beforehand. Next slide, please. So we take a second approach, which will resemble a little bit what is done for Zurich. So we make a vector-based distribution of city scale emissions. In this case, we do not use the country level emissions, but really the data that is available on the city scale. And then we map these emissions onto the line, point, and area sources that are within the city. You see here on in this figure an example of the 3D city model from Munich. So you can use information on buildings and roads and everything that's in there to map these emissions. And you can add additional information, for example, traffic count data to increase the level of detail and improve the quality. I'm not going into more detail about this. I think that Dominic will spend some more time on this type of inventory. But what I want to point out is that the downside of this method is that you use city data, so there's no necessarily consistency with country level emissions. Next slide, please. So this is basically a plan for the inventory from Munich. Now I want to spend a few words on uncertainties. I'm now seeing the presenter mode. I'm not sure if everybody's seeing presenter mode or.
Yes, we see your next slide, but not anymore.
Yeah, this is great. Good, thank you. So I want to say a few words on uncertainties. Uncertainties are actually a very important aspect of emission inventories, and they're often overlooked. These uncertainties are needed both for MVS studies, but it can also really help to estimate a range of possible outcomes from climate actions. So we first need to know what is the source of these uncertainties. Well, actually all parts of the inventory can contain uncertainties. So there's uncertainty in the input data, such as the emission factor and the activity data. Especially the activity data is very interesting in the case of cities, because let's say that I fill up my car with gasoline. If you're building a country level inventory, it's safe to assume that I actually also consume that fuel within the country. But for a city inventory, this is not necessarily the case. I can easily drive my car outside the city, and any emissions do not take place within the city boundaries. So this is something to take into account. You need to make assumptions on this or use other types of data, and that introduces an uncertainty. So then we end up with, if we multiply this fuel statistics with the emission factor, we get the emissions for the city that we then downscale in space and time using proxy data. And the proxies themselves can have an uncertainty and their values, but also the relationship between the proxy and the activity, or proxy and emissions. For example, in the case of traffic counts, you cannot just simply assume that there's a linear relationship between traffic counts and emissions. There are other factors that play a role, like driving behavior or car fleet composition. And if you do not exactly know this relationship, that will introduce an uncertainty as well. Next slide, please. So the final question then is, how do we quantify these uncertainties? Well, a relatively simple and robust method is a Monte Carlo simulation. You basically take the uncertainty and all the input data and then propagate it to the final product. And we have done this for European domain. You see the figure at the top right showing the uncertainty ranges for different sectors. And you can do this for the city scale as well. The main challenge, though, is how to deal with uncertainties in spatial and temporal data, and then especially correlations in that uncertainty. For example, if I would use population density to spatially distribute emissions from residential heating, in general, we assume that in the densely populated area, emissions per capita are less. So if we use a linear function, we will overestimate the energy consumption in these densely populated areas. Now, the population density itself is correlated between pixels that are closer together. So this error will also be correlated. And you can take this into account by including a correlation length, which is very interesting for MVS studies. And I want to illustrate that with the figures at the bottom. You see two, let's say two variables that have a spatial distribution. And on the left, there is a very short correlation length, and on the right, there's a longer correlation length. And you see that if you have a longer correlation length, there are clusters of pixels with similar characteristics. And you can use this information very well in MVS studies, because you only need to know information from a few pixels to also have information on neighboring pixels. And this simply reduces your degrees of freedom. Now, this type of work is relatively new and still in progress. So it's something that we will also focus on in the PAL project, because we think this is very important. Then I will stop here and give the floor to Olivier.
Maybe we could have here a couple of questions already from the audience to Ingrid, if there is any. This is Katri speaking, so please raise your hands in the Zoom. Should you have a question? I don't see any raised hands. Do you see raised hands, Claudio?
No, it looks like there is no question coming up yet. So I think we should continue with Olivier, and then we will take questions at the after Olivier's talk or at the end of all three talks. So please, Olivier, all yours.
Thank you, Claudio. I'm Olivier Perrussel. I work at Paris on emission inventory management and development since 2006. I will present here a few slides regarding challenges we can have using local energy, local data in the emission inventory construction process. Next slide, please. So first, let's begin with some general information about Air Paris emission inventory. We build a regional emission inventory at a city scale for 1,300 cities in the region Île-de-France for more than 40 pollutants now. And from 2005 to 2018 for the most recent emission inventory we have. So we can make emission trends for all pollutants we have. Our temporal resolution is annual, but we can have monthly emission inventory or weekly or even hourly emission inventory, because we have a temporal profile for all activities sector. And we use a bottom-up approach with lots of local data. So I will present you 3 examples now of using local data and challenges we can face. So next slide, please. First example of local data is energy consumption data provided by energy suppliers. We have data at city scale for several activities and many energy sources. These data are very interesting because they are very precise, but we have nevertheless some challenges to overcome with this data. First example is about incompatibility with other data sources. For example, natural gas consumption for industry sector in a small city in the east of Paris called Zurich. For this city, we can see the local data in blue, and in red, the data provided by the large industry in the city of Zurich. So we can see the difference. Second example is about dealing with statistical secrets. It is an example for Lodi city and the residential sector. We can see that we have local data for 2015, but we don't have for 2018 due to statistical secret. So the question is, what can we do for 2018? Next slide, please. Thank you. Another example with this local energy consumption data is a challenge with validating historical data. An example here for a small town in the south of Paris called Chalmaison. We can see that the trend is very special, with a huge increase from 2014, followed by the huge decrease from 2017. So we can wonder whether this trend is valid or not, and what kind of validation element can we have to ensure that this trend is valid or not. Last example is a change in sector scope from one version of data to the next. It is an example for the city of Paris, and you can see the share of electricity consumption data between residential and tertiary activities. Residential are in red and tertiary in blue, and we can see that the share is very different from version N and version N+1. It is due to a change in perimeter. That is to say, a small office space at the bottom of a residential building was counted tertiary activity in the N version and not in the N+1. So it makes the differences. Next slide, please. So the second example of challenges using local data is about the road traffic sector, and especially challenges regarding the consistency of historical road traffic emission. But to better understand this challenge, let's talk briefly about our road traffic emission model. We have more than 200 typical situations of road traffic in the region. One is about, for example, traffic during holidays. The second is about traffic during Sunday, and another one can concern road traffic during peak hour, for example. All these typical situations are given by regional surveys, such as EGT surveys, for example. And every hour, we correct this model and the typical situation with information given by traffic loops. Traffic loops gives for each hour a number of vehicles, speed of vehicles, and so on. We have 700 traffic loops in the region, 500 in Paris, and 200 in the outside Paris, in the rest of the region. So we can have each hour road traffic and road traffic emission. But the challenge is about the availability of traffic loops, especially outside Paris. Here is an example for a small city called Limours in the southwest of Paris. We can see on the picture 4 traffic loops in red, and near the study area in blue. And these 4 traffic loops are taken into account in the emission calculation for Limours city. But we can see that there is a lack of consistency, and the lack of consistency of the historical data emission is due to the perturbation concerning the traffic loops availability. Next slide, please. And the third example is about local data for tertiary activities. These sectors include many different activities, such as offices, shops, bars, health and social establishment, and so on. And we use the number of employees or students for the specialization of emission from these sectors. But as you can see in the slide, in the picture, compilation of number of employees depends on many databases, and the issue is that each database has its own perimeter and is its own period and so on. So it is very difficult to have a clear evolution of employees for each city and for each subsector. So we have challenges to have a consistent database, and challenge with also achieving comprehensiveness of the data. So to conclude my brief presentation, I would say that using local data is very interesting for our emission inventory, to have a more precision in our emission inventory. Local data have a real interest for our emission inventory to approach the reality. but we have also challenges, as you can see, with this kind of data, especially for small cities, because generally for Paris and other bigger city, local data generally are well represented with this precise data. So I finished. Thank you.
Thank you very much, Olivier. Very interesting talk. I think we have Stavros. He tried to raise his hand. Stavros, would you like to ask a question?
Yeah, it was for Ingrid for the previous talk. It was about how you can actually she talked about the downscaling of the spatial domain, but what about the temporal? I mean, how can you use these inventories to have, for example, hourly variability of your priors?
Yes, thank you. That's a very good question. In principle, it works in the same way. You can do temporal downscaling the way you do spatial downscaling, but it all depends on the resolution of your proxy data. And in the case of temporal downscaling, you would need data that has a high temporal resolution. But it works in the same way, and if it all depends on data availability, I guess. But I do see a shift towards more and more data getting available, also with increasing resolution and more open access. So I think there are great opportunities there, and it's a good way to start if you do not have the detailed local bottom-up data.
No, thank you.
Is there a other questions? Question for Olivier or for Ingrid for that matter? Then please raise your hand or speak up, put it in the chat. Seems not the case.
Hugo has raised his hand, Claudia.
Oops, sorry, I missed that.
Hi, Olivier. Yes, this is Hugo from TNO. I have a short question to you. So, for example, houses and roads, they're quite stable. So the road will be there. It's a historic fact. The house is often old, but some of the sources in the city are actually not stable. For example, building sites who then attract during 1 or 2 years, maybe a lot of machinery, and then go away again. How do you deal with this? Do you get data from the municipality on that on a regular basis? Or it's an open question, but yeah, maybe you can say something about that.
Yeah, of course. Hi, Hugo. It's a huge challenge for us, because we have statistical data for building sites, but they are not updated, and we have a very well, yes, we have a lot of challenges to determine precisely the number of the special vehicles and special public works equipment, and so our calculation are very global, not so precise, because we have difficulties to get up-to-date data.
Thank you. Yeah, I'm obviously asking because we find it very challenging as well. So we can share.
Yeah.
Sure.
Right, we should move on. Yes, Dominic, floor is yours.
Hey, thanks. Welcome also from my side. So maybe we go to the next slide. Okay, so I will talk about the emission inventory of the city of Zurich, which is as Ingrid already mentioned, a vector-based emission inventory, a very detailed inventory. I'm giving this talk also on behalf of the city of Zurich, which has provided a lot of the material of my talk. So next. Now, maybe to start, I would like to mention that the city of Zurich has, like many other cities, an ambitious climate action plan. Already in 2008, the city or the population of the city voted to reduce the energy consumption per citizen to 2,000 watts and 1 ton of CO2 by 2050. So that was quite a long time ago. More recently, the city has decided to take a net zero path by 2040 for direct emissions within the city and a reduction by -30% for indirect emissions, which are more difficult to control for the city outside. And the city administration itself takes an even more ambitious plan to go to net zero by 2035 already. So the city has issued a large action plan with 57 actions on the building sector, energy supply, mobility, and so on. The lower right hand of what is shown on this slide is quite interesting because the city has estimated that the emissions, the direct emissions from the city that occurs within the city is only about 1/4, but there's electricity consumption, electricity produced outside of the city. There's other consumption by city population, and that makes up about 75, so 3/4 of the emissions of the city occur actually outside of the city. And the emission inventory of the city only that is dedicated to the emissions inside the city. So important to keep in mind. Next slide. Here's an overview of the relative share of different emission sectors to the total CO2 emissions in the city. So against common belief, or traffic is not the dominant factor. So it's about 20% of the emissions are from traffic, that's this blue. And most of the emissions occur from heating systems, and even the 2 waste incinerators within the city have a larger emission than the total road traffic. So next. So now I'd like to talk a little bit about the emission inventory. Here is just a map, a 10-meter rasterized representation of the emissions. The scale goes up to 5 million kilograms per year, but there's only very few points. That's basically those waste incinerators which have these large emissions. So most of the figure is just orange and red because it's in the more intermediate emission range. The emission inventory is produced every 5 years at the moment. In the future, probably every 2 years. As I mentioned before, it only reports emissions, direct emissions within the city, so-called Scope 1 emissions. It's of course an important policy tool for the city itself, and it has a spatial resolution of at least 10 meters for area sources, but most emissions are reported as line or point sources. Next. So it's really detailed emission inventory. It reports emissions for 9 different air pollutants, for particulate matter, NOx, CO, SO2, ammonia, VOCs, soot and benzene separately, and 3 greenhouse gases. So methane and N2O have been added very recently. I don't know much about that, but I know more about the CO2 inventory. The emissions are reported not just as a total, but actually for 65 individual emission categories. You can get line, point, or area sources for all these categories. And here's just a small table which is part of those sectors. And on the right-hand side, just an overview of the broader sectors, so traffic, heating system, industry, commerce, agriculture, and even natural emissions are considered. Okay, next. So here's just an example of 2 of those 65 sectors. So here's, for instance, emissions from car traffic. So traffic is divided in different types of traffic, and here's just an estimate of emissions from car traffic. So in the inventory, there's an estimate of traffic density per road of emission factors according to Handbook for Emission Factors. So taking into account the type of traffic, whether it's cars, trucks, and so on, the slope of the roads, the speed of traveling, and so on. So next. And here's an example for the heating emissions, and only from gas heating. So the inventory separates between oil, gas, wood, stoves. Gas is quite used abundantly for heating. And the city knows for each house whether it's using oil, gas, or wood, or it's connected to a district heating system. And here's just a representation of the point sources from gas heating. And actually, we know the exact position of all those chimneys and also at what altitude the emissions occur. Next. And then, of course, in the final inventory, what we use, for instance, in our models, we combine all those sources into a total of all the sources. So, I mean, there's a lot of detail in how this data is collected. Olivier mentioned there's a need for a lot of activity data. The nice thing of the city inventory of Zurich is that's produced by the city itself, and the city has access even to what Olivier called secret data, which maybe someone else would not have access to, and that's really makes it special. Next. We've used already something like 5 years ago this emission inventory to simulate NOx concentrations in the city with a high resolution, 10-meter resolution dispersion model. There was work done by Antoine Bercher and others. And here's just an overview of the NOx distribution contributed by different emission sectors like cars, heavy-duty traffic. On the upper right, you see the contribution from buses. There is interesting that within the city center, there's electrical buses, so they don't emit any NOx, but outside we have diesel buses which emit NOx. So this is just a glimpse of the detail level of detail of this inventory. Next. So finally, I would like to talk a little bit more about temporal variability, and Stavros already alluded to that. What is reported in this emission inventory is annual emissions, but in order to use it in atmospheric transport model, we would like to know the emissions hour by hour. And so we need temporal disaggregation. And what has been done a lot in the past is to use standardized temporal profiles for seasonal, day of week, or diurnal emissions, which you see on the right-hand side in these figures for the different types of sectors like traffic, heating, and so on. So heating demand obviously depends on weather. Industrial emissions are lower when there's public holidays. The traffic varies over the day. So there's a lot of variability that needs to be taken into account. Next. And so because we have such a detailed spatial inventory, we would also like to have detailed information about temporal activity. And our colleagues from the urban energy system at EMPA have started simulating the energy demand of each individual building in the city. So we know there's a lot of information about the type of building, its age, the material used for construction, how well it's insulated, and so on. And then they use an Energy Plus model of the US Department of Energy to simulate the energy demand, taking into account actual temperatures, radiation, and wind conditions every day. We are now in the process to combine this with the emission inventory, where we have detailed information about whether it's gas or oil heating system in order to compute, and also the CO2 emissions at every hour and from every building. Next. And another problem is, of course, traffic, which varies a lot. And already Antoine in his work didn't use the standardized TNO profiles, but looked at traffic counters, traffic loops within the city. There's about 90 counters in the city. And he did a cluster analysis of the behavior of traffic at these different counters, which you see on the right-hand side. So there's a lot of places where we have this classic double peak with a morning and an evening rush hour peak. But there's also locations like in the lower right corner where traffic is just rising in the morning, stays almost constant throughout the day, and decreases in the evening. And those sites are actually those in the city center. So you have outside the center, you have the commuting, but inside the city center, you just have the whole day more or less a constant traffic. So that's gives an impression that it's using one single factor might not be, temporal profile might not be enough. Next. And of course, where we would like to go to is to use even more real-time information. And in the realm of COVID, there has been a lot of GPS or mobile phone companies trying to generate mobility data, like here, the Apple COVID-19 mobility data. I just downloaded this figure yesterday for the city of Zurich. It shows how mobility evolved since the start of the pandemic, with this decrease in the beginning and rising later on. So, and there's also mobility data provided by TomTom. That's actually a commercial product. But one question certainly is, how accurate are those data sets? And there has been a nice study from the group of Jiachen, which you see some results on the right-hand side, that there's actually a rather large uncertainty in these products. So here's a comparison of the Apple mobility data in blue with the TomTom data in red, and governmental data, which is actually the traffic loops in orange. You see fairly large differences for this monthly evolution, but then also in terms of the day of week evolution, that for instance, the TomTom data report a very strong decrease on Sundays, larger than reported, and Apple has almost no decrease. So there's certainly uncertainties that we need to better understand. But I think that's certainly the way to go, to use more and more real-time activity information. And next. So yeah, to conclude, it's a very detailed inventory that we have for many air pollutants and greenhouse gases. I think important is that it's produced by the city itself, which has already this large collection of statistical data that is needed to produce such a detailed inventory. We have already used it for dispersion modeling. One thing that is missing is kind of a rigorous uncertainty analysis for this emission inventory. So we have this detail, but we don't know very well, or we know very little about the uncertainties of this inventory. And the spatial and temporal disaggregation is key for atmospheric modeling. And I think for temporal disaggregation, we still need to take a next step, and we are working on that, but it's still preliminary. Next. So with that, I'd like to conclude and thank especially the city of Zurich, which provided a lot of the data, and my colleagues that provided data and figures. Thank you.
Many thanks, Dominic. Very nice. So far, I don't see any raised hands. If you have any questions at all, please. There is Stavros. Please, Stavros.
Hi all, thank you for the very interesting talks. I have a general question actually to all. I heard in the previous talk by Ken Davis that at least in US there is this inventory called Hestia, and has I'm not sure, I haven't really used or seen this product, but it seems to be a very very good one. So it has for all cities of US or something, and hourly standardized format emissions. So is there something similar or in preparation for Europe?
Kevin Gurney was on the call before. He's the main person behind Hestia, but I think he left because it's probably late in the US. So to my knowledge, there's nothing similar planned for Europe. So I think that's certainly an issue that probably each city takes its own effort to produce these data set. It's also not so easy to, as you know, a lot of these activity data is very locally available, and in Switzerland we have different cantons and cities, and they all collect their own data sets. I think it's really challenging to produce such a kind of European-wide city emission inventory approach, but certainly would be nice.
Yep, thank you, Dominic.
And then we have Alex, who has raised his hand.
Yes, thanks all three speakers for the nice presentations. I have a question for Dominique and maybe also for the rest. It looks like in the emission inventory that you presented, this is only for the Zurich city itself. So and I know Zurich a little bit. There are a lot of cities, let's say, immediately surrounding Zurich. So are you working also on getting more detailed emission inventories from these other cities or villages?
Yes, actually, the canton of Zurich has also an inventory, not as detailed as the city, but also quite detailed, and we collect also those data sets. But unfortunately, as far as I know, there's no inventory yet for CO2. That's only for air pollutants. So for CO2, we probably need to rely on a Swiss-wide inventory, but which is also available at 100-meter resolution. So that's what we can use.
Okay, that's good. And the national emissions, you didn't say much about that, but how is that handled in the city inventory?
Good question. I know that some of the data sets in the city that they take from the national inventory and do a downscaling, if they have no local activity data, but most of the emissions are computed locally from local activity data and emission factors. So there's certainly some inconsistency between what the city reports and what the national inventory reports for the area of Zurich. And we haven't looked at that yet. Was that your question? Or?
Yes, thanks.
And then we have a question from Yvonne. Dominic, are you able to see special events like fireworks, or are you able to follow up on political measures that were implemented to verify that they actually reduced emissions?
Yes, well, fireworks is certainly an event we see very nicely in the measurements. I'm not quite sure. I know it's in the inventory, firework emissions, but I don't know exactly how that's computed, whether they just take this standard Sylvester and Swiss national holiday fireworks, or whether there's more detail behind that. I don't know, but it's in the inventory, but the temporal allocation is then, well, not that difficult, because we see that very clearly in the measurements, air pollution measurements. And political measures, that's something where I mean that there have been in 2006, I think the last time, some strong air pollution event where political measures have been taken, and so that's lately we didn't have this kind of intervention, but certainly political measures on let's say spatial planning, that some certain districts are expanded or roads are closed, that's taken into account in the emission inventory.
And for Paris, we are able to take into account special events such as Marathon de Paris or Journée sans voiture, without cars. And because we have our traffic model, and with this traffic model in near real time, we are able to log several roads and to calculate emission due to this event. So we can do that for road traffic emission.
Thank you very much. Then we have Veron, who would like to ask a question.
Thanks to all presenters for your very interesting talks. I would like to open the perspective a little bit towards the whole project. We are intending to put a lot of measurements on into the 3 pilot cities, and for me it would be interesting to ask you how these measurements can improve your approach. You have told about uncertainties you have told about some problems with the data compilation you have. So what are you expecting from these measurement arrays to support your approaches?
Who wants to go first?
For me, it's a very good question, but I think measurement can allow us to identify some spots, some hotspots that maybe we cannot have yet in our emission inventory. And I hope also that with this measurement and with the inverse modeling, we can have another view of a CO2 emission budget of Paris, and it's a good way to compare this data with our existing emission inventory.
Yeah, I think one data set will be these eddy flux measurements, and then so I think certainly we will try to compare those with the where we do have the footprints of these eddy flux measurements and compare with the emissions within the footprint from our inventory. I mean, the way that let's say emissions from a heating system is distributed, it's basically considering the size of the burners in the houses, but then currently the insulation of buildings is not yet considered in the emission inventory. So it's a very simple distribution over the city of the emissions, and that's certainly something we could test a little bit with these eddy flux. And with the other measurements, it's more like Olivier said, it's the city-wide emissions that we then compare with the emission inventory. I don't know how much we can break that down into local, district level emissions or sectoral emissions. That's to be found out. Certainly the target will be the total emissions of the city, or at least, in Zurich it will be more the parts of the city.
Thank you very much. Well, our is basically up. I am happy to stay for another couple of minutes. We have Ingeborg and Sam raised with their hands, so I don't know about the speakers if you have to leave or not.
5 more minutes is fine, yeah.
Okay, then Ingeborg, Sam, you have hopefully only a short question. Ingeborg.
Yeah, I also want to thank the speakers for their interesting talks. And I had actually a very similar question as Werner, because I'm always asking myself, what can we really improve or help the inventory to get better or more accurate? And the question was more or less answered. Is it better to have many sensors distributed over the city, or to find hotspots which have not been known before? Or is it better to go into the plume? I think it's a fundamental question, and maybe it's very hard to answer.
I really hope that by the end of the project we have a better answer.
And Sam, with the last question before we wrap up.
Yeah, thank you all. I have only a short question. What about those approaches of smart cities where you get direct activity data from heating systems, for example? Are there any approaches also to take those data into account when you do the emission modeling?
Yeah, I think certainly what I mentioned, to have this real-time activity data is a goal. I mean, smart cities is a big word. And there's a lot of attempts to use this Internet of Things and have real-time information. So I think at the moment, maybe we are a little bit in an intermediate step that we take, let's say, these traffic counters, which is already a very useful information. We are in contact with Swisscom to get mobility data from that local mobile phone, Swiss mobile phone company. And but then the really hard thing is industrial emissions and heating emissions. For the heating, we take this approach of explicitly modeling the heating demand of the buildings. I don't think there's any, at the moment we don't have information on actual energy consumption by the individual buildings. So a smart city might have that in the future, that on each of the burners that there's kind of a direct measurement that's reported to the city, but at the moment we don't have that.
I agree. We in the Netherlands, you have these, we now start implementing these smart meters in buildings. So you can monitor the electricity consumption or gas consumption per building. But there's a problem with privacy. You just don't get that data. Even if it's anonymized, you don't get that data. So it's somewhere, but to use it is a different question.
Okay, thank you both.
So last but not least, to Olivier, there is one question I have missed regarding the events like Journée sans voiture. Is it consistent with air quality measurements? The very last, quick one, sorry.
It is a very good question, and it depends on the events, because if we take the Marathon of Paris, there are many roads that are blocked, and so we can have in Paris measurement, and we can compare measurement and the result of a traffic model. But if we speak about Journée sans voiture, there are only some roads that are blocked, and we have not the measurement in the roads surrounding the event. So it's difficult to evaluate the model in this kind of situation.